Can you see this? Is that clear? Coming up?
Yep.
Can you see that? Jed? Yep.
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 Maybe.
That looks good.
I'm writing too many programming languages recently. Can't remember comments syntax.
Best thing about Zoom is everyone can like get as close to their screen as they need.
Yeah. I don't need to do 7 rounds of plus and minus. Hopefully. I can't hear you, Tim.
So is it QuickCheck or that's typo?
Pardon?
Kind of. I thought it's Hedgehog, not QuickCheck.
Oh, yeah, so it's kind of funny. So what I'm actually going to do is write a very, 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 very basic property-based testing library first. And it's going to be closer to QuickCheck than Hedgehog. But then I'm going to write on top of that essentially what is Hedgehog's state machine testing.
All right.
To the point where you'll be able to copy and paste all of your code and it'll pretty much work. Minor changes. And the goal is that we're just going to smash through the first bit, which is implementing our QuickCheck. It's not going to have shrinking because for start, shrinking gets a lot more complicated when it comes to state machine generation, state machine testing. So I'm not going to do that just because it adds a lot of complexity that's not really useful in understanding how it works. So the biggest difference between QuickCheck and Hedgehog is how they shrink anyway. So we're not going to do either of them. So it's pretty simple. And then we're going to bash out essentially the way that Hedgehog does its state machine testing, which I think is better than the way that the QuickCheck state machine guys have done theirs.
Sounds good. Sounds good, yeah.
Cool. That's the plan. This is actually, I did 2 talks for my colleagues at Simple Machines, where the first talk I wrote essentially what is this QuickCheck version, and then I added shrinking, and then I changed the shrinking into Hedgehog style integrated shrinking, so that they'd understand that first. And then the next talk we did the state machine bit, but we're going to just go through both of them. Yeah, we're going to skip shrinking and go all the way through.
Are you ready to start, Hugh?
Is everyone back? I can see a bunch of people. Did everyone just hear the little spiel that I did about what we're going to do? Feel free to turn your cameras on and throw thumbs, or turn your mic on and say yes.
Well, I can vouch for hearing it.
All right, cool. All right, so hi, thanks everyone for letting me come and talk. It's a real pleasure. So as I said, this is a bit of a recap of two talks that I did recently, talking about QuickCheck, Hedgehog, and state machine testing. And the way that we're going to do this is, first of all, we're going to write a very quick and dirty but simple property-based testing library. Okay, so, and then we're going to talk about state machine testing and what it is and why. But I think just to start, I'm just going to say the thing that I think separates state machine testing from standard property-based testing, and it's this. In normal property-based testing, what we're doing is randomly generating arguments to give to functions, and then we're testing properties about the results that those functions have, right? So properties of the functions that we're generating random arguments into. State machine testing is slightly different. So the way that I like to think of it is, instead of generating arguments to functions, we're generating programs, including all of the hairiness of that. So we need to keep track of the program's environment and all of its variables and all of those things, right? So we're generating big, hairy programs which can run in parallel and do all sorts of interesting and wonderful IOE effectful stuff. But while we're doing this, we've got some mental model that allows us to comprehend what's going on. So what I've done is essentially stolen a dodgy circular buffer implementation off the internet. So it's a circular buffer, right? And you can initialize it with a certain size, you can put things in it, you can get things out of it, and it's great. And I've wrapped that up in with a little bit of Haskell, and then we're gonna test it, okay? And if I was to be a Java programmer or something, I'd write something like this, okay? So if I was to unit test my Java, my circular buffer, I'd be doing something like this. I'd be creating a buffer. I'd be putting some stuff into it. I put in a 5 and a 10 and a 20. Then I get something out, and then I make sure that the value that I got out is 5. Okay. This will probably type check depending on how you want to play things. But this program is very different to this program, where I've created a buffer with length 2. Right. So here I've got a 5 and a 10 and a 20, and I've put them all in, but this time I get it out and it's 10. And we've all got a mental model for why this is working, right? So what's happened here is the 20 has overwritten the 5, the tail's clicked around, and we've read out the 10, and that's fine. But when systems get more complicated, writing these tests becomes a lot harder, and it becomes very difficult to write enough of these effectful programs that we'll be able to do well. And this is where state machine testing can really shine, because essentially, instead of running these things against a mental model, we encode our model and we generate and we test all of our assertions as we run along. All right. Cool. Does that sound, hopefully that sounds interesting. All right. So let's get started on actually writing a basic testing library. So essentially, we're going to have something which is a generator, and a generator is pretty much looks similar to a reader mono. It's just a function, takes StandardGen, and gives you back an A. All right. Okay, so a generator is a function, is a data type which can generate values of type A. So generator A can generate values of type A given a standard generator. It's pretty simple. It's got instances of HFunctor. This is exactly the same as what it would be for the reader. Essentially, we just need to create another generator which can take the seed and runs FP-SYD. Cool. It's got instances for applicative as well. This one's really boring because here does nothing. spell instance. And we're just going to use the other one. What have I done wrong?
I think you need an equal sign on the line with F19.
Yeah. And pure is return. Sorry, monad is the only one where it gets a little bit interesting in terms of the base classes, in that the first thing we do with our seed is split it. So StandardGen has an operator over seeds, which can make 2 seeds out of 1. And there's been a little bit of research into them which says that this actually does work, and it gives you back very random results off both sides of this. So we need to run the generator of the value that we've got. But then we also need to apply F to that. And then we need to run that again. And okay, cool. So that's how.
Is that meant to be seed 0 and seed 1?
It is. Thank you.
Okay.
Bit of a bug if it's not.
It's the same as the reader monad, except that instead of duplicating, you split.
That's right. It is very similar to the reader monad. But that's, yeah, that's exactly the point. Instead of duplicating it, I split it. And the reason is obvious in that if you want to generate multiple integers, you don't want them to be the same integer. It would defeat the purpose of property-based testing. So what we're going to do is just bash out a couple, which I mean very much, not very many, 3. Quick generators. So we can make a generator for bool. So the normal way that StandardGen works is when you call random, it returns a new seed and the random value itself. You can probably see it. So it returns a bool and the StandardGen, a new StandardGen, which is different to the one that we've just run. Because our bind operator splits the seed itself, we don't need to actually use the standard generator that this produces. So we're just going to take it away. So we also want a quick integer one. So it's pretty simple. So all we're doing is using the fact that random has an implementation of this already for us. The reason it's not carried, don't know why. I would have carried it. And the last one that we're going to want is element. So element takes a list of A's and gives you a gen of A. And it's pretty simple. We don't need to use gen notation here, but we will. So essentially what it does is selects a number between 1 and the length of A's plus 1. Selects it up. This is obviously not the safest function in the world. It'll crash on an empty list, but we're going to pretend. It doesn't matter. If your tests are broken, your tests are broken. You'll find out when you run your test suite. All right. So now we want to talk about what a property is. Okay. So we're running property-based tests. So essentially, a property in this framework is a generator. Okay, so it's a generator that gives me back something, whether it succeeded or failed. And we are going to use one of the things in that QuickCheck has that Hedgehog doesn't, which is the testable class. But we're not going to do arbitraries because Hedgehog doesn't have them and we don't need them. And yeah, it doesn't make a lot of sense for us to add those. The only reason we're doing testable is because it means that we can lift booleans immediately. All right, so testable is something that says the testable property is a function that, given a prop, gives me a property. All right, so we have an instance of testable bool. We have property. Yeah, so it just lifts up the boolean. All right, and we'll have one for property as well. It's just ID. Okay, and now we can talk about generating values to give to functions. So what we want to do is write a function called for all. And this is, I'm sure we all know exactly what for all does. But given some property, if we can get a generator of A and an A to a prop, and give it like a property. Okay, so for all is a function, takes a gen and some F, and it needs to produce a property. Right, and all we're going to do is go gen. I'm going to bind this generator to, well, we need to get let's go those first. Got an F of A. That's not quite right. So we need to lift the result of this into a property because we've got prop, so we want to run property on it. And then we also need to think that this is actually returning now a property, but this is a gen, so I need to run property. Bring it back to a gen so that we can bind it against the gen. Nice. We can get rid of it. Just go. Does that make sense? Yeah. Someone needs to say yes. Oh no. No, it's fine too. All right, I got
Yes.
Thank you. All right, and then we've got a function called check, right? And what check does, it says if we've got a testable property, you give me a value of that property, I'll give you an IO of bool. That's why we'll actually run your test for you. So I'm going to actually use a monad. And what we want to do is run this test 100 times. Right? So we're going to write a sub function, go, run a single pass. That's going to take an integer, which is the number of tests left to run, and the seed that they're going to run it with. All right, so go. If we need to run no more times, we just return true. Go at any other number. We're going to split our seed again. And then we're going to run our property with this seed. Okay, so this is relatively straightforward. We need to run the property. We need to lift the prop into a property. And then that gives us a gen. So we now need to run the gen. We need to apply that to our seed.
You just need the fat rocket on the type signature check.
What's that, sorry?
So you need a fat rocket on the type signature for the for the function. Yeah. No.
Yes. It's a constraint, not a argument. All right. So if we succeeded then we run again, we recurse with the split seed. So we want to use a different seed each time we run. Otherwise, we return the result. Right. And then we can finally start. So we need a new StandardGen to start our whole thing, and then we go 100 with our starting seed. And that should type check. All right, and we should actually be able to run it. All right, load FP-SYD. So for all Booleans, they're not true is false. They are true, or they're not true is true. Okay, so we've written the world's most basic.
Here we can't see your terminal.
Oh, you couldn't see my terminal. Oh,
No.
okay. I'll bring one up here.
That's all right. I believe you that it works.
It does work, but it's okay. I can bring a terminal up inside code, or I can't.
Your desktop.
I need to share my screen a different way. But we can write properties, so we can say, you know, for all bool, it goes to B or not B. Something like that. And that's fine. For all, doesn't matter. So that's the idea. So we can now check our properties. Unfortunately, it's not extremely useful at the moment because when we want to know why something didn't fail, all we're getting back is that it's false, which doesn't help very much. So what we want to do now is add a very basic reporting mechanism to what we're doing. And the way we're going to do that is essentially, instead of returning a bool, we're going to return a result. So we're going to type a result. Right, and a result is either success or it's a failure. There's some reason for why it failed and also a bunch of inputs that went into it. So the results, the things that came out of our for all. Okay, we're just going to write a few helper functions. So if we go fail with, there's a function that takes a string, gives you a result. And essentially it just goes failure. And we want to have one more thing, which we want to be able to add an input to a result. So we want to be able to take a string, as in an input from a for all, something that was output from a for all that went into our creating the error that we saw, and map it over a result. And this is trivial. If it's a success, it just stays a success. End value D. And if it was a failure, there's a reason and some stuff. We just want it to be a failure with the same reason, and D cons some stuff. Writing too many programming languages recently. Good cons is a single column. Silliness. All right. The only other real thing we want to do is be able to map over a property with a result. So if we go map result is a function that given a result to result, which is this one, property. Some function, and that's over property. And well, we need to create a property. It's to start with something that runs the property. Right, so I've got a hole here, it's of some type, which is given a gen bool to gen bool. We'll just fmap it. We're pretty close. All right, I know what I've done. It's a single F now.
Do you
Yeah, let's see,
also
I
want
wanted
your
to-
property to be a gen of result rather than a gen bool?
Yeah, that's what I want to do. I want to change this. So actually what I want to do is, instead of just going result, I want to go IO result, because I want to be able to run something here. FNAT, that, and that should be fine. And then when we want to do testable, it needs to be gen of IO result. So pure, lift it later. It's going to be return. With that's enough. All right. So that okay, cool. Does that make sense? So essentially, I'm just still lifting this property up. Okay, and this one is now wrong because that returns an IO. It's pretty close. Result. Okay. Okay, so that's pretty good, apart from the fact that we still won't be able to see what the inputs were. So what we need to change is our for all function. Okay, so instead of just running the generator, we want to record what it was. Okay, we're going to do it with a show instance just for fun. So A is the result of our gen. Map result, add input, show A. Still need to run this properly, but we'll do it outside. Okay, so that should work now. So what we've got now is a very, very simple property-based testing library, which will perform tests and tell us what went wrong when we execute properties. So we'll say what the inputs were that caused things to have an error. All right. Are there any questions? No. Cool. All right. Yeah, it's pretty simple. All right. So back to state machine testing and the way that Hedgehog does it, because this is where it really gets more interesting. But hopefully someone learned something from that little exploration of how to write a basic property-based testing system and how they work and what they are. All right, so back to this example. So what we've got here is two programs which I've written. And the way that I've written them is I've got some mental model, which essentially says that I can figure out where the two pointers are, and I can imagine them on a clock face, and I can sort of track them around and go, oh, well, I'm over here now, and I'm butting up against this one, so I'm going to click them both around at one time. This one can go backwards when I retrieve data out of it, and all of that's fine. But some things are too complicated to keep in your head. So we want to get a computer, we want to get our program to write these programs for us. We want to get our testing suite to do this. All right, so when you think about what we need to know in order to generate this, we have to have a mental model for what a circular buffer is, and that's fine. We also need to record, like, I created a buffer, so I need to know I created a buffer, and I need to know that I gave it a name, which is buffer. Right? I need to know what I put into it, so I need to have some record as I'm going along. That I also need to know what I did put into it. So I need to update my model based on the fact that given some buffer that I've already created and actually exists yet, I need to be able to know that I can get a value out, and then I need to be able to refer to the value that I did get out and check it against what is in my model, my mental model for how this works. Okay. When we want to run it, we need to be able to reify these things. So I need to actually call create, but then every time the buffer is referred to further down the program, I need to be able to instantiate it with the real pointer to the real buffer, which I've used, or the real data structure in a Haskell, in my Haskell program, which is just a pointer to some C structure in real life. Right? And the same with this retrieve value. I need to be able to run these puts and this get, but then actually grab out this retrieve value and use it. Okay, so what we want to do when we're generating these and running them is have an abstraction for these terms. Okay, so when we're generating them, we don't know what their values are because they haven't been run yet, but we know their names. And when we're running them, we don't care what their names are anymore, but we know their values, right? But these are all the same type, right? So this is a buffer, right? And this is a number or an optional number, because if you can get out, you can call get on an empty buffer and get a none, right? So they're the same type, but they hold completely different things. All right. So the trick we're going to use for this is called higher kind of data types, right? So these are parameterized by a higher kind, usually a functor or an applicative. I'm just going to be using the functor instance here. But here I've created a higher kinded person type, right? So a higher kinded person has some functor type H, right? And the name is an H of string. And the age is an H of int, right? If we know everything about them, then we can say a known person, this is just a type synonym, is a higher kind of person with identity, right? An unknown person, if we don't know that we know everything about them, then it can be a higher kind of person with a maybe.
That would be a perhaps known person.
Pardon?
That would be a perhaps known person.
Perhaps known person, yes.
Unknown person would just drop all the data on the floor, right?
Yeah, I could have void.
Void, yeah.
A null person.
Or const.
Yeah. So people do sometimes doc person. Right. Which is a high kind of person. Const string. Something like that. And that's fine too. So this could hold like the names of the fields, right? But it still fits into this person parameter. So yeah, the value for name would be const name and not actually have an A at all. Right, and we can move between various higher kinded parameterizations, right? So if you give me a higher kind of person of identity, and I can give you back a higher kind of person, maybe. And that's fine, right? And we use these things in like parsing situations. So if you've got data coming in out of JSON, then you'll have like some validation step. So you can have your record be parameterized by maybe when you're parsing it, or by either when you're parsing it. And then when you want to reify it, you can traverse over it and get back the error for why it didn't parse properly. So it's very useful abstraction to use. All right. So we want something. This is fine, but we want a general abstraction that goes across these. So what we use is called the HFunctor. There's also a library in Haskell called Barbies, which calls it a B functor or something, functor B. It's a silly name, but it's the same principle. So HMAP is a function which parameterizes over or swaps out the higher kinded parameterized type of our HFunctor, here our HK person. So if you say for all A, if you can give me an M of A, like an M of A to an N of A, then I can give you a G of M to a G of N, okay? So we can compare this to hoist, which it looks most similar to, but in hoist, which we use when we're talking about swapping out the type under a monotransformer, these are still parameterized by the A, right? So G would be a monotransformer and a monad. And of course, map looks similar, except again, these A and B type actually appear in the type of the F and the G itself, whereas in our higher kind of functor, we don't actually have the results or the held types inside them as a type parameter. All right. So the implementation of HFunctor is usually, well, it's extremely simple. So we can say HFunctor of high kind of person. And we just want to implement this function HMAP over this high kind of person that has some namey type and a thingy type. And it's just calling F on both of these. And because F is parameterized on for all A, here F is working on M of string to N of string, but here it's on M of int to N of int, right? So it's parameterized over the type. All right, so now we can write to unknown again, which is a function which takes an HFunctor to maybe known, and an H of identity. I'm using like an H of maybe. It's just HMAP. Strip off the identity in each value and wrap it in a just. Right? And we could also do something completely naff. That'd work too. You normally wouldn't do that, but that's fine. So we can use these things to strip out the boilerplate when we want to do traverse across multiple terms and work across multiple types. But obviously some things are easy, like going between identity to maybe, but going from maybe to identity is a little bit more tricky, right? We can only go from maybe to identity if all of the terms are just, right? So we can do it maybe, right? So we can write HFunctor maybe, which is for all A, M of A, blah, 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 blah. But this is not the most general term for this. So we can actually write H-traversable, which generalizes this maybe to all applicatives. Okay, so we can return an either here, or it doesn't really matter, but anything. So it says for all M and N, which we had before, but also for all applicatives, if you can give me a function for all a between m of a and e of n of a, so this is my applicative term, the maybe, the can I actually perform this transformation, and you give me a g of m, so an h kind of person, higher kind of person of identity, or a h higher kind of person of maybe, you can maybe give me back a higher kind of person of identity. Okay? This is a pretty complicated type signature, so we'll go through it one more time. So for all a, if you can give me a maybe to maybe an identity, if you can give me a higher kind of person of maybe, I can maybe give you back a higher kind of person of identity. Okay? So this is the machinery that I'm going to use to parameterize my input values as I generate functions with my concrete values as we execute our programs. And this is why when you use Hedgehog, you'll often find yourself needing to write this little bit of boilerplate on all of the types. Okay, and it's completely mechanical. There's actually only one solution for it. There's even, I've got a little port up where I'm auto-generating it, like deriving it with generics. So it is mechanical, but it is useful for this purpose. So at the moment, you still need to write them yourself. So now we can write to known, right? And known takes a H traversable. Given a maybe, gives me a maybe of a higher traversable of identity. Right, and the way we do this is we call HTraverse. And again, we've got what we've got is a maybe of something. And what we want is a maybe of an identity of something. So what we do is just fmap identity, the identity constructor, right? And we're done. Okay. So hopefully that makes sense. So we got Hedgehog also uses a free or a simple trivial high kind functor, which is called var, or variable, which represents a value, a name in a program, a variable in a program, a binding in a program. And it is trivial. It is a variable of a parameterized over h is just a new type with the h wrapping the a. You can turn it into a new type. Same thing. Right, and it has values for HFunctor and HTraversable. All right, so here's the plan. In generation phase, what we're going to do is give everything a name, right? And we could come up with fancy names, but we're not going to bother. We're just going to give them incrementing integers. So the first variable that we bind, the first binding that we create will be 0 or 1, and then the next one will be 2, and then 3 and 4. Okay, so every function that we call will create a new binding value. Some of them will be unit, and we just don't care, but that's fine. So blah, that doesn't matter. But they'll all have names. Okay. So during generation phase, this program will become this program. So create 3 will bind it to variable 1, and then we'll use variable 1 all the way through the rest of our program. 2, 3, and 4 we won't use. We probably won't even store the fact that they exist. They won't go into our mental model for what exists in the universe. Variable 5, we will use that when we want to check that it conforms to our mental model. When it comes to running this program, we're going to substitute these just phantoms with actual values. Okay. So the first thing we need is a name. We're just going to use ints. And yeah, it's just a type synonym. I don't care. All right. New type. So the first thing we want is a functor which just stores names, right? So this is just type symbolic. That's a naming thing is equal to const name. Right. We can also do it as just a new type or data. Data symbolic is symbolic name. Okay. And so it's just a basic data type. Free. So it's just a data type parameterized by an A, but doesn't actually hold it. And then the other thing we want is just the identity functor. But we'll give it a new name anyway, because Hedgehog does, and we're going to stick to the nomenclature. So we call these concretes, and concrete is, it just holds the value. It doesn't do anything special at all. Right, and then we're just going to have a little helper function which allows us to grab out a concrete from a var. Sweet. And that's really simple. So all we've done is created two new functors. We've just given essentially const string and identity. Nice and names. Yep. All right. So now we have to run commands. All right. So we want to be able to describe commands. So commands are the thing that we tell our generator that it can do, right? Okay. Oh, well, that's failing immediately. Figure it out. All right. So what we need to be able to do with when we want to run our program, imagine what we're doing is not when we want to run it, when we want to generate our program, we've got some mental model that's going on, right? And then we want to be able to go, I've got six different actions, six different commands that are possible, right? Can I do this one, right? So up above, my commands are create, put, and get. I can only create one when I don't have one in existence. I can only put one when there is a thing to put into, and I can only get when there's a thing to get from, right? So we need to have in our mind our state, right? So what commands parameterize over is the state, our mental model. But they don't care about what the input is or the output is, or they abstract over, they existentially quantify the inputs and the outputs. So a command which adds two integers, right? So it takes two ints and returns an int, is still just a command. It's not in its type that it records that it takes those things, okay? So you can have a list of commands that all take different things and return different things, right? But what they need to take in is a symbolic state, right? And then they give us back a generator with the inputs that they take, or the input that it takes, okay? But as I said, sometimes it's just not possible to run this command. So what we actually do is we maybe return a generator. And we want to have a function which executes them. So command execute is a function which takes an input, right? But it doesn't take a symbolic input anymore. It needs the real values. So this is going to be a real IO action. that returns the output from the command. Okay. So our, if we've got the put command for our circular buffer, the input is the buffer and the output is, well, it's unit, right? It doesn't return anything meaningful. But if the command is get, for our get command, the input is, again, the buffer, but our output is maybe an integer. It is that's what this output type would be. Right, so it takes a real concrete buffer and gives us back an output, a real value. And this was the command execute would be where you'd put your FFI functions. All right, and as I said, we have a mental model for what's going on. And what this does is it takes a state, but it can take either a concrete state or a symbolic state, right? It has to run over both because we have to be able to run it with when we're generating and also when we're executing. So what we do is we quantify the type of state that we're running over. So we've got for all states B. If you give me an input, remember input is an HFunctor, right? So there's a high kind of type. And an output B will give you a state B. So we're updating our state in both the real world and the symbolic world. So we update our mental model and then we update what we really expect, what the real state is as we run the program. And then we have our tests. So some commands, when we run them, we expect them to actually hold. So what we do is we take the concrete state that we finished with, or we can go with where we started with. We go to the concrete state we started the execution of the program with. Yeah, we'll do both. The input state, the final state, the input, the output, and result. Okay. And that's how we specify what a command is. And this is very similar to what's in Hedgehog proper. There's more types with the generator monad and the monad test and things like that. They don't just use IO and a bunch of extra little bits and pieces, but if you can understand this, you'll be 95% of the way there. There's also a require step, which is used in shrinking to make sure that we don't do anything naff. All right. So when we generate these, we're generating them into a concrete. So after generation, this is what we use to generate. But then we've got an actual set of values that we're going to run, right? So this is to help us generate it, but we want a set of actions that we're going to run. And it's almost an exact copy. The biggest difference, the only real difference, is that they're all called action. So we've now got an input, and that's just an input, right? It's already been generated. It knows how to execute. It knows how to update. It knows how to output. The other thing it's got is a symbolic output. Okay, so this is just the name. Okay, so what we're going to do is move from taking a list of generators and generating me an action or a list of actions. And this is what the program, my specification for my program is. right? So action is, again, parameterized over this, my state. It is given some inputs which are computed from my state, right? Give me some values dependent on some variables which you've already run with. I'm going to give you the next incremented variable. I'm going to execute. I'm going to update the program, and we're going to ensure that everything is all good. Okay, because we're going to report what's happened, we need the show instance.
So if I get what you're saying, these action data types are going to be generated according to the specification laid out by command?
Yeah, so what we do is we say, here's a list of commands, right? You've got 20 to pick from, or 3 to pick from. Randomly generate them all, right? But when you reify them, you're not just going to have the generator anymore, because what the generator gives you back is an input symbolic. So we rewrap these things in an action type. And the action is the concrete data type, which is going to be the thing that gets run. So you get a list of actions and you're going to run them all.
Okay, so command is like the gen and action is like the A.
Yeah, so command is my specification for each of the things that I can do. And my list of actions is my program. Right, so this
and does the symbolic output come from like just a fresh counter or something?
Yeah, that's exactly right. So bar 1, bar 2, bar 3, bar 4, bar 5. This is not an action. This is part of this action, right? Which is why I've put them on different lines. So this is the ensure for this action. These ones have trivial ensures, which don't actually check anything. Yeah, hopefully that makes sense. So for our show, we don't really want to do very much. I can't show these, like they're all just functions. So essentially what we're going to do is just go, look, it's a var, show the output. Then show the input. Right. I've got like var has a show because it's trivial. What's output? It's just a name. It's an integer. So I can show the integer and I can show my input because I've ensured that I have a show instance for them, right? But then essentially they're just like do stuff. Okay. This is going to look ugly. We'll do a show list as well. That's right. I don't remember how show lists goes. Yeah, shows. It's just shows. Yeah, combine it. All right, that'll be fine. Yeah, I've got it there. So now what we want to do is generate. So we need a function to generate. So as I said before, a list of commands is our specification for all of the different thingamajigs that we can do. So we can create, we can put, we can get. We can only get when there's a buffer, right? The input that the gen function will give us back is the buffer's name. Yeah. All right. So what we want to do is generate an action. We're just going to give it a name here. So this is our fresh name. We've got a symbolic state. we have a list of commands which can examine that state. And what we want to do is generate an action with parameterized over that state, obviously. It's going to have some name, state, and all right. So we need to find the ones which will work. All right, so let possible actions, possible commands. Yeah, this is pretty tricky. So
I imagine it would be the ones that return just.
That's right.
For
so we're
the
going to use a
generator thing.
list comprehension. So I go just gen. So we need to gen the state. Oh, we need to get all the commands. So commands. So we need a command. Command gen. Where's it go? Where's it go? Yeah. Commands. Yeah. And then I'm going to filter those. Yeah. Let's run that. That needs to be run against the state. All right, that's fine. And now we need to know these things. So that's what execute, update, ensure. Yeah, all right, so this is annoying. So what's happened here is these things are existentially quantified, but tuples aren't. So we've got to copy this.
Can't you just return the command constructor applied to its arguments?
But then it's got the maybe still. And it's got the state still.
Okay, yeah, you want that input variable, okay.
Yep. Okay. I think that's what we want. I think Hedgehog proper does this differently. Yeah, I think it does something slightly differently. I think it just calls from just somewhere. I'm not sure. So I think it does do exactly what you said. It doesn't matter particularly. So now we need to pick one. So not a command, a generator. Yeah, it's a generator for the command, for the thing, for the actual thing we're going to pick. Let's use these names again. Element. I made element for a reason. That works fine. So now we've got a generator. So now we've got the inputs is just by running that generator. And now we can return the action. That's this junk. Oh, and the name. into rapid and symbolic.
Is it fair to say that when we're thinking of this as a state machine, the commands are like the transitions?
So I guess the command, so the commands, the transitions are probably the update functions. So if you think of it as like a graph of all different states, then the commands would be the edges that go between all of the different nodes, and the actions that we take as like the path through our graph. So if you've got this sort of very large quasi-infinite graph of different programs that you could write, then each edge would be a different reification of commands, or a different action that you could take. Yeah. All right. Now that's how to generate an action. We just need to generate a bunch of them now. So generate actions. Be similar. It takes some state. And yeah, list of commands, and see back in chain of actions. That's right. All right. So the first thing we want is the number of actions we want to run. We need to generate integral. Apparently there's a GHC proposal up at the moment to make it so that you don't have to put undefined on your do blocks when you're doing these sorts of things. Let's go. Some number.
Yeah, underscore, right?
Pardon?
Underscore.
Oh, I think they just want to make it so it continues to parse.
Oh.
What's going on there? Into state. Oh no, I need to put the state there. It doesn't like that. Yeah, whatever. I think that'll be solved. It doesn't know it. Yeah, doesn't know which integer to pick, but we'll get that later. So now we want to be able to run that multiple times. So we're going to fold we're going to fold some function. We'll go do it later. Stuff. We want to start with our initial state. And we want to go just all of them. Okay. Go. Oh, we need to generate a list. What are those? What are those? Okay. Takes the rest of them. What's already been generated? State we're going to work on. Name. And yeah, calls gen actions. Gen action. We need to update a state. And apply to the state. Is that it? And an output. What have I done wrong there? Sorry, that was really annoying. Existentials, they don't allow you to do that for some reason. We got input, output, execute, update, symbolic. Execute. Yes. All right, that makes sense. So that's how we generate our programs. So we need to actually do it now, don't we? So we just go, what do we return? Just the actions. Oh, we're reversing. Yeah, they get done, they get made in reverse order. All right, let's go to the next statement. Is it the first one? We don't need the final state. All right. So that's the idea. So given some initial state, we can, and a list of commands, I can generate a program that we're going to properly test. When we want to run this thing, we need like an operating environment, right? So, you know, if you think about closures, right, they enclose an environment. And when you think about what an environment is, it's kind of like a list of names to stuff, just anything. So that's what we're going to use. So when we're running a program, we've got an environment. So let's try that. So an environment is a map from name to end. So we're going full dynamic typing here. Unfortunately, it's a bit hard to get around it. So Hedgehog proper uses data.dynamic and a little bit of extra stuff. But then it just essentially just throws you an error anyway at some point. Like it just gives you back an either somewhere. So it doesn't really matter too much. We need to construct them. New environment is an environment. It's just map.empty. Let's go. Right. So relatively simple. And now the really tricky bit is this is a map, right? From a name, but it's a symbolic name. It's a symbolic value for a thing. But what we want is the concrete value that we've put in there. Right? So we want to reify our environment. We want to pull our thing out given our name. Right? So we've got a symbolic. A. So A is a real type, right? And what we want to get out is an A, a concrete A. Concrete's just the identity functor. We don't even need it, but we'll leave it there anyway. So this is const name, but I've got the type. I know what the type is because this has a type attached to it. And I'm giving me back a thing. So I've got an environment, symbolic, the name, and I can go and give me it out. It's like, no.
Because it's a map.
Button, no.
So could you maybe get away with a dependent map from symbolic to concrete?
So where would you be able to put the types? I was just going to do this.
Let's put that question for later.
Hedgehog proper does from din. So symbolic stores a little bit of exponential, so that says that it's typable. So it's got a typable constraint on this thing, so it's not actually just a simple new type. Yeah, Ben. Hi, you've got your hand up. Are you leaving? He's gone. I thought he was answering a question, but he was just leaving. He left directly after unsafe coerce. How rude. All right. The other fun thing we want is we want to be able to update our environment. So given an environment and a symbolic, environment, let's just put it in the bloody map. Like it's not, none of this is complicated. But this environment thing, I think it actually maps quite well to the way that we think about the way that real programs actually work, right? In every dynamically typed language, at least, that map of that environment map is a real thing. In some languages, you can even get it out. Our concrete is an A. We're going to be putting so like they really do have maps of any. So I don't think it's the worst thing in the world. You might disagree. All right. So this is all of the machinery that we need to be able to then run our program and check its outputs. Okay. So we've got environments. We've got a way of describing, not this one, a way of describing both our mental model, we just parameterize over it, how we can generate different commands out of it, right? So we just select one of the gens that happens to work at this point in time. We've got ways of executing them, updating our mental model, and parameterizing all and running our tests. So what we think should happen. We've got the internal representation of our program as a list of actions. We've got ways of generating individual actions and sequences of them, ensuring that our state is sane all the way through. And we've got our environments. Right, so now we can write executes. We'll just start with a single action. What do we get? We need an environment. Yeah, we need an environment. We need a state. Concrete state. Generic result. Let's just try to write this. My notes get a little bit fuzzier down the bottom. So we've got a state, we've got an environment. So we can let our input. Let's we missed action. Okay, so we've got an input, but it's still symbolic, right? So we need to reify the input itself. And now we're finally going to use HMAP. It's going to reify with the environment, the input. Okay, so now input is an input concrete. So I've mapped, I promised this at the start, I'm pretty sure. I've mapped over my input symbolic, which is a higher-kinded data type, with HMAP to get an input concrete. This function is not actually total. Hedgehog proper uses htraverse, but I've pretended that it's total by using unsafe QoS and just, yeah, the names in there, trust me. So Hedgehog proper doesn't use either of these. It puts them into an either type and will give you back a particular error. They don't occur in practice. So I didn't do that, but that's a difference. All right. My output is going to be what I get when I execute my input. All right, so output is of type output. It is a real value running inside IO. Okay. I've got a new environment. So I've got an update function. Oh, yeah, that's no. So what I want to do, so I've got a new environment which contains my outputs. Yeah, so I've got a new environment. So I need to update my environment. Starting with the initial environment, the symbolic output name, and what it actually is. So the value that I got out from running it, that's now entered into my map of name to any. And I've got a new state as well, where I run my update state function from this command. That's a type state to input to var output. So I've got a state. It's a concrete state. I've got a concrete input. I've got a concrete output. Output. QuickCheck. That's just a value. It needs to be wrapped in concrete. Okay. And now I need to return a result, but I need to return these as well. Yeah, we won't do that.
What's the purpose of passing the concrete output to update?
So the concrete state, when we run update, we need to update our model for what's going to be there. It can't actually look at the values in particular while you're updating it, but while you're checking, it can. So you can say things like, I put in var6, right? You can store the fact that I'm holding on to var6. var6 is something that is real, right? So you can imagine it's like, I did a database query and I got back var6, right? But when I run, and then later on, I'm going to check that var6 is equal to something. But when I run it, I actually get out a name right? And then I can check that that name was equal to something. So update is polymorphic on the HFunctor itself. So we can't look at it while we're running update, but we can look at it when we're generating, because we can look at the names, and when we're checking, because we can look at the values. Hopefully that makes sense. So what I'm doing here, I need to return a new state and environment. So I need to start with a state and environment and return a state and environment as well as a result. All right. So I'm just being a bit lazy and getting these out of state. Okay. And now we're going to put them back in. State. And now we can return. Oh no, we want to. So we want to run our ensure function. So ensure takes gives you an eye of results. So we need to do a lift because we're in state T now. Right, and this is our actual property-based test, or our check at the end of each time we run a command, we run its ensure after we're done. All right, and ensure is a function that takes an input state and an output state. Doesn't really matter. It could just be one. State. We're going to do it the way that Hedgehog does it. Takes input concrete, so input prime, output concrete. All right, so that's how to execute an action. It is run a step of my program. That's what it is. Go through one line, make sure all of the properties that I know about it hold. Okay. And then we've just got one more step, which is do all of them. And it's going to look pretty simple, hopefully. So we've got an initial state again. It's going to be a concrete one because we're actually going to run these with a list of action parameterized by that state. We've got a property. That's what we get. So I could probably do it with a fold. I don't know. We'll just do it manually.
You can traverse it.
You should be able to traverse it. But we want to. Our result doesn't short circuit. Our result's not a mono.
Yep.
It's made a helper. So we'll start by saying we've got whether we're successful or not, and we're just going to recurse only if the success is held onto. So just like we had go with 0 and 1 before, we're going to go the rest of my program. So we're going to run this function. So this is the result for this step. That should work. We're in state T here. Then yes. If it's not a success, or it's not a, or it's the empty list, then we return the result. Right, so we only continue if it's currently successful. So far, everything has been successful and there's more to do. Otherwise, we return with what we've got so far. So if it's successful, but this is the empty list, then we just return success. Otherwise, we rumble on. Yeah. All right, so we are gonna do a state T. So exec, exel, eval, which one is it? Eval. I think it's eval. Eval state T. Property is an IO of gen. So we need to start by saying we're actually generating a property. So we're making a property. We're gonna get out of our state T. Oh, we don't need the gen anymore either. It is a gen, but we've already generated. That's a property, yeah. I think that's right. Eval state T, where we start with our initial actions. Flip. Initial state and a new environment. And then we run our action, we start. All right. Okay. So does this make sense? So we don't need a seed because we've already done our generation, right? This is what we use in our for all. So we go for all, bar, generate all of my actions, and then we pass it on, and for all takes a prop. Okay, so we don't need either of those things. We could probably even just return result. I'm not sure, but we need to do IO. We had a prop for IO of result. It'd probably like fun as well. Celebi. All right. So we're in state T because at each step we need to take a state and an environment. We're starting with the initial state and the initial environment, and then we're just running through all of our actions, but short-circuiting on a failure. Yeah. And that is it. That's all we need to be able to use it. Okay. So fortunately, I have a test using it. Okay. So this is how you use it. And this looks almost exactly the same as the Hedgehog version, which I've also got here. We can put them side by side once I've talked you through it. Okay, so we're doing a circular buffer. I think I showed, oops, the C code, or at least I showed the C header. I've got it wrapped up in a little bit of Haskell code. So my circular buffer is a foreign pointer to, doesn't matter. It's just a pointer. I do exploit it. I probably shouldn't. I can create one which calls the C function init. And then I put it into a foreign pointer, and I put a free on it so that it'll get collected properly. And then I only really do 3 commands. So I've got get, where I malloc myself somewhere for the data to go, do a bunch of marshalling, blah, 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 blah. It doesn't really matter. Given a circular buffer, it gives me a number back. I've got a put, which is given a buffer and a number, runs it. I've got another put, but this one will not overflow, right? It won't overwrite. It'll stop and return false, right? And that's it. I've got 4 functions. Okay, so I've got a model for this. Okay, circular buffer. So it's got a capacity. I've got a variable, a var, right? This is a higher kind of functor for one of these actual circular buffer things. And then I've got what I think is in the buffer at the moment, right? So the contents of the buffer. And this is just a list. This is my mental model for it. You could do this better, but it doesn't matter. Because of course it doesn't have a capacity until you create one. I can only create one. It doesn't have a contents until it's created. So you could probably do it as a map instead, or a map of vars of circular buffers to capacity and contents. That would also work and probably be better, but it doesn't really matter. So my initial state is I'm not holding one. These two are just dummy parameters. It doesn't matter. I can create a buffer, right? So this is a command. Okay, this is my parameterized version of what a creation is. So the command create with a size is, this is what I'm going to build. And this is my command for it. So the create command I've parameterized over, actually what this is the input. So this is my parameterized input to the create function. So my create command is a generator that says, I need to have no circular buffer created, right? If I've got a circular buffer already created, then nothing. Otherwise, return a generator which will create a buffer between 1 and 50. Right? And where we're using this is here. So, right, it's a symbolic state to a maybe gen of input symbolic. My input is this create data type.
Okay, so the reason why update gets that output is because you're keeping the actual thing alongside your mental model of it.
Yeah, so my mental model for what I'm going to put in is what I have generated, this action that I'm actually going to put in. I know what I'm putting in because it's part of the program. Right? So if we look back at our program, I'm putting in 5 and I'm putting in 10. Right? And I'm creating a buffer of size 3. So this is a program. It kind of mixes between what's input and what's not. This is the input. This is the execute for it. But you can think of it as this is it. Right? So when I say generator create, when I go to execute, I take a create and I call circular.create. So they kind of map 1-to-1 with commands and inputs to commands.
Yeah, just looking ahead, is there an advantage in doing it this style versus creating a sum type for your inputs? So create, like instead of having a separate type for create and put, you could have create or put.
So remember that the not all types take the same input, and I need to be able to parameterize, like existentially quantify that and hold it. So I don't think it'll work.
Sorry, not all types take the same input.
So if I were to have
if you added the put constructor to this data type, yeah. Well, it would probably take a var circular buffer or something as well.
Yeah, it would. I'm not sure if that'll work. I'll have a look into that.
Okay.
Interesting thought. Anyway, so we say that our command we'll build one of these integrals if we've got one of these. If there's no buffer, its execute actually creates it, and its ensure action, which is this one, doesn't do any actual checks. It just returns success. Put takes the var of circular buffer and the number that we're going to put in. It's also got an HFunctor and HReversible instance. When we run put, obviously we can't generate a put if there's no buffer. If there is a buffer, remember that our state is holding here. This is a symbolic state, so it's holding a symbolic var. We can call put on with an like we're just going to put in a number between 0 and 100, and execute takes the concrete var, pulls out the actual circular buffer type pointer, and calls the underlying C function to put the value in. And now our contents function, our update function, essentially calls take with the capacity and then cons on. So it's just making sure that we're not going to overflow. Actually, it looks like what I'm doing here. Yeah, no, it's contents equals take. So I cons it on, and then I make sure that it didn't overrun. So I'll drop things off the end. Right. So I put it on, and then if it's gone 1 over, then that last 1 over 1 will disappear off the top, off the end. And that's what I think I'm doing. But notice that I'm not clicking multiple pointers or doing anything fancy. So my model for what's going on is actually very basic.
This is why we can't sum them, because execute has a different output type between put and
that's right.
And create. Yeah. Okay.
Yeah. And get is similar again. So get takes a circular buffer. Again, we can't run get if there's no buffer, but if there is a buffer, then there's nothing else to really do. It's just a pure function we can do. Again, when we call get, we'll be able to actually, when we call execute, we're going to be able to reify it and have the actual concrete value, or it's going to be reified for us. So we can use the underlying C function, and then here's our command. So our state, we're going to drop, essentially remove the head, I guess, but safely. So we're going to call init safe init. And our safe last function takes a, all right, because we take from the other end, of course. So we take all but one values off. If there's none left, then if there's none in there, it doesn't do anything. So safe init just is take the length -1. And safe last is give me a maybe back if the list is if there are values in the list. Otherwise, give me none. I want the last one. So we drop the last one, and if safe last contents is equal to the output that we actually received, then success. Otherwise, we fail with an error message saying that what we actually expected to see is not what we really got. Okay, and then here comes our test. So our test is for all generate actions, initial state, create, put, get, execute these actions, initial state. Notice these initial states are actually different. So this one's symbolic, this one's concrete. It's a polymorphic initial state. And yeah, this is just a main runner. Okay. I'll try and share a terminal. Share. All right, can we see this?
Yep.
Test. Have a main attached? No. It doesn't. Oh, there we go. Okay, so here's a failure. As I said, we didn't implement shrinking. So it's a little bit bigger than it should be. So 23 is not equal to 31. I've got a bug. Okay, so I created a thing with 3. I did 2 gets, which did nothing at all. I then put in 14, 12, 23, 31, and 9. My buffer's 3, size 3, so I should have gotten that out on the get. Oh no, I got out the 23. I should have got out a 31, but I didn't. I got something else. All right, so my C implementation has a bug in it. Unfortunately, I read it a long time ago, so I can't remember what that is. But c'est la vie. I can try to find it. Where are we? Share. Okay. Okay, so we can have a look at our circular buffer implementation. I've probably got a comment somewhere. There we go. So I've got some, if the buffer is full, then we're going to increment the tail. But we didn't do that correctly. When we called this advanced pointer function, so we messed up. We didn't increment our tail properly. So that led to a bug, and we found it pretty quickly. Okay, when it comes to what Hedgehog looks like, it's extremely similar. Hopefully this will work for us. Should run both. Yeah, so I haven't done my cabal file right. If you care, I'll fix that. If you don't, I won't bother. What did I call all of my files tonight?
Call what?
Oh, because I've rewritten this like 6 times and I always put different files in. So I've got different versions of it. So I've got FP machine, FP-SYD. I don't know which one that it actually was using is the problem. I'll change the test so it uses the one we just wrote, which was FP-G. I think that's tonight's version. We don't have print result. I missed one function and something else. I don't have show. So I missed a few show instances. We'll put it back. Go with the one I know exists. Port. Yeah, I've rewritten it 6 times, so everyone's different. But we can not show that one for now. I'll show the Hedgehog version because it looks very similar. Ah, damn it. All right, we'll have to miss that. Sorry about that, I didn't prepare well enough. It essentially looks exactly the same. The biggest difference is that it prints nicer and it shrinks. And it can also allow you to do find more interesting bugs because it has parallel property tests. So if you look at the commands that we've got, they're almost exactly the same. The biggest difference is that instead of taking each execute, update, ensure, it takes a list of things and the things are parameterized by update, execute, ensure, and require. Not everything needs all of them. So Jacob essentially said you can pass as few or as many of these as you like. It's pros and cons on all things. The property tests themselves look a little bit different because Hedgehog doesn't do for all in exactly the same way. So it does it in form of a property monad. So my property wasn't a monad, but it's pretty much the same. We generated commands. We'll do them side by side. Split.
Can you post your code after this so I can look at it when I'm less sleepy?
Yeah, sure. It is on GitHub currently, but I think it's private. But we'll do that. So as you can see, everything looks almost exactly the same. So it gets pretty much identical. And the prop is pretty much the same as well. We execute our actions with state. We generate actions given some, this generate actions just generates a number. It's got a range of them. Its initial state, it's got the get, create, put. The interesting thing is Hedgehog also has this parallel type. And what this does is it generates a small starting set of actions and then 2 branches to run in parallel on different threads. And this is used to find things like data races or race conditions in your code. So my circular buffer doesn't have any locks on it. And it will do different, when it calls a put, it'll advance pointers at different points in time. When you call a read, it will get it out and then change the pointers. And there is realizable delay between these two. And if you interleave the actions, then you can do things like get a pointer out and then read it again. And it will find these sort of bugs, these bugs where locks really needed to be used, which is extremely difficult to do normally. The other really nice thing about it is it'll show you all of the commands, but it'll also show you what it got. And the reason that I say that it's really nice is because I implemented it. It was my contribution to the library. It looks great. Anyway, I can probably show you an example, but yeah, if you look at the PR for it, it does look nice, and it really does help you find out race conditions, which can be really difficult to solve normally. All right, any questions? Comments? Interludes?
Hey, Hugh. Just maybe one quick question. Have you heard of state chart?
State chart? No. Similar to TLA?
Meant to be an upgraded version of state machine, but I was wondering if that could improve the test, but never mind.
Okay.
So I've heard of state charts, and we're using Lustre at work, which is, I think, similar in some ways to state charts.
Using what, sorry, Hannes?
We're using a programming language called Lustre.
Oh, yeah.
Which is, well, Lustre with the state machine or the automaton extensions is similar to state charts, I think. I think they had come from a similar background of a similar time in history that they were developed in.
So I think there's a very interesting jewel to state machine testing, which is TLA style model checking. So if one of the ways you can design programs is to, especially if they're like complex distributed things, is to model the very core without any of the complexity of like, hey, it's a network, or it's, you know, what's being stored or anything like that in TLA. So you model things like messages, and it'll go, well, this message can go before or after this one, right? So I can send this and this, and I can send a message and I'm expecting a response, but either of these sides can fail. And this guy's going to update his state when he receives, and then he's going to send it back. But if it fails, are we going to reach a consistent state eventually? Does that make sense? So these are like your descriptions of your properties in Hedgehog. But what it does is make sure that your properties actually make sense, which I think is really cool. So you could use TLA to create a model for the way that it should work, and you'll be able to enforce particular properties on it. Like if I were to write it in actual programming code with this overlay, or like in this way, then I will not ever reach an inconsistent state, right? My eventually consistent will actually happen sort of thing. And then you can actually write those properties back out as QuickCheck properties to make sure that your implementation satisfies the real properties that you wanted. And you might even be able to share a bit of the model. It'd be very interesting, I think. Anyway, look up Taylor. It's good. It's fun.
My question is, I'm looking at this hammer and I'm trying to figure out what the nails look like. So we've seen like testing data structures and seeing that certain things, like seeing that the APIs make sense. I I can imagine you could model your own little distributed systems in it. What are some other examples of maybe some unconventional things that I could test with this?
So anything that's got any form of sort of like remotely stored state or distributed state would probably be a really good good place to look. So you could imagine that you've got a machine which is examining bunches of data from and stores bunches of data on S3 and has a state file to say, you know, what I've already done and what I did with it, how I'm going to process it, and what's going to happen. That would be reasonable. Probably a bit of a big hammer on that case. The other one is if you don't actually have access to the code, you can still create a model for it. So we modeled a circular buffer written in C, but there's no reason that I wouldn't be able to test a library which I was linking to, right? A stateful library. So something with quite complex state, even. So like you could do SQLite. That would be totally reasonable. SQLite already has one of the most exhaustive test suites in the world, so it's probably a bit of a waste of time. But the Erlang guys did a few of the distributed databases that Google was putting out, and they did find serious issues. And essentially, what happened was they encoded their model, they ran it, they found bugs, they reported them to Google, they fixed those ones, they ran it again, the exact same code, and found a different suite of bugs, right? That had been uncovered because the first suite were fixed. So things like that. Like obvious use cases, but really any stateful system. And like as pure functional programmers, we try to not write a lot of those, but they are out there.
So yeah, I've used it on command line tools that talk to remote things like S3 or some other data store in Azure. To just wrap those up and generate things that run a separate command in another language.
Yeah, so it's these, you know, when you're writing programs and there's like that bit at the end, which is like all of the statey bit, and you test all of your functions, you're like, it's a bit tough. I'll do three CLI tests and that. Yeah, it's that bit.
When you're talking about interfacing with like external data sources, is that the execute function that's going to call out to those and get results back? Yeah, okay.
That's right. So the execute function in Hedgehog proper, it's parameterized over a monad, which is monad IO with a bunch of stuff. But you can also hoist to get it down to sort of anything you want. So if you need to change the monad, you can run underneath that sort of thing. So it is quite powerful. You could do AWS really easily, but really any IO action should be fine.
The state space of transitions in a finite state machine can grow very, very quickly. How do you know that you're traversing a representative subset of that and not getting stuck in a corner of the state space?
Interesting question. So one thing that Hedgehog has, which I also fortunately had the pleasure of contributing to, is a bit of coverage metrics. So you can look at your actions before you execute them and label them with some form of coverage. But you can also really adjust your generators, right? So you know what your generators are, so it should be relatively simple to think about how your generators will exploit the state space. But yeah, if that's not enough, then you can do coverage checks as well.
I
So you
also
could do,
stupid things like just adding bugs and making sure that it finds them.
yeah, that one's pretty simple too. It's a nice thing to do, that one.
Well, the
Makes
mutation testing like that's not stupid.
Yeah, no,
there are things for
like,
automating those.
You do want to like, when I write property-based tests, I always like to have one dumb test as well, and then I will make sure that it fails at least once, and then I will be comfortable. It's just it's not unreasonable to put one normal style unit test in and one expect failures test in, and then cover the rest with property-based tests. I think that's reasonable. Yes, there is coverage. It's not too bad. Cool. Did everyone enjoy that?
Yeah, awesome. Thanks, you.
No worries.
Thank you very much.
If you could share the code, that'd be great.
Yeah, because I've got like 7 versions of them. So the way that I originally did this was with like diffs. So I had them all printed out. Like I had pages of diffs, and I'm like, oh, this would be easy. It wasn't.
The hedgehog sauce?
Pardon?
Isn't just hedgehog sauce. Like that's the one, ultimately you should go look at that and then go, oh no, that's a bit hard, but yeah.
Well, that was kind of why I did it this way, right? So
it's great.
Especially when it comes to Hedgehog's implementation of its properties tests and trees. It's actually kind of complicated because there's a property T monad which wraps a test T monad transformer, which wraps the tree T monad transformer, which wraps the gen T monad transformer, which wraps IO and stuff. Right? It is hard. So to use just that, I think for a talk would be a little bit, it'd be a bit tough. So that's why we started with an extremely simple.
I love what you did for a talk. It was great, really, really good. Yeah, but ultimately, like you might need like a new type on top of that, and then go and look at the hedgehog source.
The hedgehog source for the state machine testing is extremely similar, like very, 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 very similar. I've put in a few. I did unsafe coercers and stuff, and I didn't type as many things, and I changed the way that the commands sort of you wrote them, just because we didn't need some of the extra things that shrinking requires, such as the require. Yeah. So, but really, it's super similar. Yeah. So if you can understand this, you will be able to go and write ones in Hedgehog now. Right? You can pretty much copy these and fix the type errors. It's that small a change.
Yeah, nice.
Yeah, that was the idea. It's not the only way to do it. Like the Scala Hedgehog version doesn't do H traversable. It's got essentially a case class which has a function called get, which given an env will run it for you, and it's got like a private name and stuff. Pros and cons to all takes. I don't find it as convincing. The R version just says that it's a symbolic variable. It's got some tag on the data type that says, yeah, no, I'm a symbolic type, so you can replace me. and that's how it works. But that's a dynamically typed language, so they're
Erlang
trying.
would be similar, right?
Pardon?
I
Yeah,
imagine
the one's similar. There is actually some advantage in that when you write your generators, you don't need to worry about like if it's an applicative string or a functor string, or you're going to put your values in. So you can just write a generator, which is like data type x is equal to gen int, y is equal to gen string,
yeah.
z is 2, and it'll just do the right thing. But there's a whole bunch of like internals going on which are a little bit opaque. So Hypothesis has an implementation of state machine testing as well, and that's quite good as well. So if you're ever using Python, use Hypothesis. It seems really good. I was actually writing some today. Not that I enjoy writing Python, but you know, I've never written Erlang in anger, but the QuickCheck one is apparently excellent as well.
I mean, the first thing we did at the start of this talk was throw away totality,
Right.
which I'm complaining about. But yeah, we said, well, it's test code, and if it fails, well, that just means the test fails. And
there is a thing to that. I did go a little bit yellow on 1 or 2 points, but generally this was quite sound. Well, where was it was the gen element. Yes.
Element, yeah. But
yes, if you give me a list of commands with no commands in them, I'm gonna fail. Sorry.
Which is fine. But I mean, maybe we should be writing our test code in Erlang or in Python, and our real code that actually executes and runs, it can be written in a nice type-safe language, but we can write our tests in Python.
So I think Haskell still has a lot of benefits. It also has one of the best runtimes available. So I did write an R port for Hedgehog, but I was like, oh, I've got the sequential testing now. I'll do the parallel one. I couldn't do it, right? Its runtime doesn't do that. You just can't do that.
Yeah.
Single-threaded languages, it's like writing JavaScript or something. Hedgehog has Haskell has excellent runtime support, and QuickCheck costs money, like Erlang's one. So if you want a good multi-threaded language for writing tests in, I think that Hedgehog is probably one of the best ones, if not they. I'm sure that Erlang has its benefits as well. It's been around a lot longer. There's also a few, I think, sneaky space leaks in Hedgehog still, which need to be sorted out. But that's something that will happen over time.
I've never had a chance to use the commercial QuickCheck. I really want to try it for testing C code and specifying C code.
I think you do. Yeah, you do really well. I'm not sure of the marginal benefit over using Hedgehog, especially because if you're writing, we write Haskell programs often, we've probably already got the wrappers for the C code that we're looking at.
Yeah.
So it's quite plausible that the marginal benefit wouldn't really be there. The only person who'd know is John Hughes probably, but he's not here.
If I were selling this to people, C programmers, I think I could sell Erlang to them more easily than I could writing this Haskell. for example. I don't think that I could go with a straight face to them and say, you got to know what an, shit, I've forgotten its name.
HFunctor.
Yeah.
What
So
the heck,
I
functor?
actually think that having to write HFunctor is a clusterfuck. And I think that Jacob agrees. When he wrote it, I don't think he believed that it was possible to write a derivation, like a generics derivation for it. It is. Like, I know it is because I've got a branch that does it.
Yeah. Yeah.
So I stole it. I didn't write it myself. I just ported. But Barbies does it. The Barbies library does it. But yeah,
having it inferred, like just having those in the type signatures, I worry would scare away the C programmers that I know.
It would just become a deriving thing, right? So you'd essentially just say input deriving Hedgehog input, right? And that'd be enough. You could probably get it down to that.
Yeah.
Like deriving generic Hedgehog input. And I think that that's comfortable enough. But yeah, half the point of this talk was to try and get people over the fact that this, you know, even Jacob says that these types are scary. I don't find them that scary. Like, yes, you need to know what for all is. Like some of these things do get a little bit long, but you don't really need to touch them, right? And the instantiation of these things is completely mechanical. So yeah, half the point of this talk was to make it obvious what was going on just by really talking through it and writing it with you. Hopefully it succeeded to a degree. But I think that, like, yes, we need to be able to talk about these things, but it is very precise. You're right. I don't, like, in Erlang, you'd have it just be like yes or something, but what is it? And what can I pull out of it? Can I pull out a value? I'm not sure.
He's not online anymore, but Eric might have had a comment to give you on comparing the Erlang QuickCheck implementation versus other things, Amos, because he mentioned some point in the past that he did do with IOHK a 3-day course that John Hughes ran, which was all about property-based testing.
I'm not sure if it was with the Erlang one, but maybe it was.
Well, yeah, so that's why I asked. He might have had, I'm not sure.
Yeah.
The possibility is there because he spent that many days with John Hughes going through it.
Yeah, that's true.
If you want to know what it's like in a dynamically typed language, I would probably recommend looking at hypothesis. So when I wrote the R port of QuickCheck, I probably went a little bit too close to the Hedgehog one to fit in with R. But the hypothesis one does seem pretty good. So and it looks more similar to the Erlang version as well.
The Erlang one's C integration really excites me, I guess, because
so Erlang, like Haskell, have a kick-ass C integration, right? A kick-ass C FFI. I'm not sure if it's R has a good CFFI as well. It just doesn't have a multi-threaded runtime.
Right.
So testing C code with R is actually quite pleasant. But you can't find race conditions using it because it can't spin up multiple threads and run things in parallel in that way that Erlang really, really, really shines. But Haskell's green thread implementation is excellent, right? It's first class. So I'm not super duper worried about that. I'm going to change the screen that everyone's on so that I can look at you while I'm talking to you. This must look like I'm bloody looking off in the distance the whole talk. Yeah, now you place it, Jimmy. All right, sorry about that.
So I know
yes.
the Erlang one, if you've got some C code and it's seg faults, then it catches that somehow. And this shrinks nonetheless. Whereas if you do the same thing in naive Hedgehog, then you're just going to get a seg fault for the whole program, which makes it more difficult to test.
Right. So I know you know how to put in a segv catch in Haskell. So maybe
yeah, that's right. Yeah. So
because you've done it.
So we did that in Icicle. We had a segfault handler that at the start of the test, it would print the test case, then it would run it, and if it crashed, if it segfaulted, it'd jump to there and take that buffer with the printed test case and print it out to disk, or print it out to standard out.
Right. So a little bit more primitive than what you think the Erlang one does.
Yeah. So no shrinking at all.
Right. Well, I think that's something that's probably tractable to solve.
Yeah. So
tricky, but tractable.
So
yeah, no, that's an interesting one.
Yeah, it is. Had an honest student, Alex, looking into it, and it's cool. The surprising thing to me was that, I guess it's obvious in retrospect, but the surprising thing was that you only need to, the only communication, okay, back up. So what you can do is have a parent process which forks, and then the child process runs as many as it can, and if it dies, it sends back up to the parent process saying that it dies.
Right.
But I originally thought that this kind of child-parent behavior would need to serialize arbitrary data structures, because you want to know what you just generated, so you need to send it back up to your parent.
Right.
But the sort of
seed.
You see the seed, yeah. So cool.
You just need the seed. Yeah. No, that's nifty.
Yeah.
Oh. That's cool. That's cool. That's a good idea. We should implement that.
Yeah. I'll see where yeah, so Alex got to the point where he had something integrated with QuickCheck that was working for testing C.
I think that there's so there was I think that Jacob has sort of complained about his own implementation or his own types for state machine generation. I think they're just in a normal state. So let's just share again. Let's move north. So here's the gen sequential, right? But if you look at command, this is the version which exists proper. Right? So this bit's the same. This bit's the same. This bit's different. It's got the bunch of cases. I've no idea what happens if you put in multiple updates. Just runs them in some random order, I'm guessing. bit awkward. I think that there's probably some very reasonable overlays that you could put on this to make this a lot nicer. Like, yeah, it's tough, but I think that this could be tidied a bit. This is the bit that I added, show output, just so we can have a look. Because I spoke about this earlier. State machine. How do you do by me? Closed work.
Isn't it author? Like it's author colon.
It probably is.
Just
it's some pull requests. Sorry. Making noises when I'm talking. No. No. Where is it?
You're telling the story.
Leave me alone. You guy. This one. All right. So this is what it looks like now when you do state machine testing across parallel branches. So this is a reading and writing references atomically. It's not atomic. Is the point. So you can create a ref, you can read from a ref, you can write to a ref, and you can increment a ref. That's all you can do. Those are the 4 commands. So the way parallel state machine testing works is it generates, as I said, a prefix branch, which is a list of commands that it runs first before it forks, and then it runs 2 branches in parallel. This is not minimal completely, but it's close enough. It doesn't really matter. So it creates a reference. It gives it the name 0. It increments the reference, right? So the reference is 1. If you were to just run this branch, the reference would be 1. Okay. On the other branch, we write 2, and then we read. Right? So the only 2 options here are that the reference is incremented first, and then we write 2, and it's 2, or we write first 2, and then we increment, and it's 3. Right? So and then we read it. So those are the 2 logical solutions, right? What's happened here is we've gotten an opaque value. It's the reference, right? It's just a pointer. Right? So 0 is a pointer. We've written 3 was right. So we got back. 5, don't give a shit about. And we read 1. Okay. So 6, where we read our value, we got a 1. Right. So what's happened is this increment does a read, read 0. This one wrote 2, and then increment wrote 1. So increment is non-atomic. right? This is a problem. This is a race condition.